Okay, here we go, folks. This is section 4-4. This is the so-called counting rules. Let me try to give you just a little tiny background of why we're looking at counting rules. Okay, so if you look back in your book on page 189, it's page 189 in the 10th edition. I don't know what it is in the 9th edition. Okay, if you look at that page, and if you're using the 9th edition, this is in section 4.1, and it is the first, I believe it's the first of the blue boxes. It's the formula for classical probability. The formula for classical probability, which is what we're going to be basically using throughout this course, is a fraction, and on the top is the number of outcomes. The number of outcomes in your set E, or the event E. So that's the number of successes. It could be anything from getting ahead. It could be anything like rolling a dice and getting an even number. It doesn't matter what it is. Whatever it is that you're looking for, the number of successes goes on top. And on the bottom of the fraction, in the numerator, or excuse me, in the denominator of the fraction, that's the total number of outcomes in the sample space. So in order for us to come up with these numbers, in order for us to decide, well, what is in the numerator, what's in the denominator, we need to know how to count, obviously. And it's not as easy as it looks sometimes. So what we need is various counting rules. So that's what we're talking about in section 4-4. In section 4-5, what we're going to do is we're going to take these counting rules and we're going to use them to calculate the numerator and the denominator of that basic fraction that we always use for computing probabilities. So I hope that gives you a little bit of motivation. Okay, the first rule then is the fundamental counting rule. Let's kind of take it apart here a little bit, try to get an idea of what this is all about. What's going on here is we have a sequence of n events. Okay, so we have n events. We're talking about events, one thing after another. For example, we're flipping a coin 5 times. I flip a coin, I flip a coin, I flip a coin. I do that 5 times. So that would be a sequence of 5 events. The first one has k sub 1 possibilities. Now that k sub 1, don't be intimidated by that. That k sub 1, the only reason we use the little sub 1 here is to just distinguish this is the first event, and then the little 2 here, I'm talking about the second event, the 3, I'm talking about the third event, and so forth, all the way up to n events. So if I'm tossing the coin 10 times, n is 10. So the first time I have I have k1 possibilities. So how many possibilities do I have when I flip a coin? I have 2. The second time, how many possibilities do I have? I have 2. There's nothing that says they have to be different number of possibilities. Okay, so hopefully that makes this notation a little more clear. So the total number of possibilities in the sequence will be, we just multiply them together. So think about it as the first time we have 2 possibilities, the second time we have 2 possibilities, so we multiply them as 2 times 2. Then the next time we have 2 possibilities, 2 times 2 times 2, that's 8, and so forth. This example here actually is a really good example because the 2 possibilities, event 1 and event 2, the number of possibilities is not the same. So for example here, example 4-38, a coin is tossed and a die is rolled. Find the number of outcomes for this sequence of events. Well, the coin, that's my K1, that's number of possibilities for the first event. K1 is 2 because I can have 2 possibilities. I have a head or I have a tail out of that first event. That second event, K2, there are 6 possibilities. So that's what he explains here. The coin can land either heads up or tails up. And since the die can land with any one of 6 numbers, there's 1, 2, 3, 4, 5, or 6, that means that there's 2 times 6, there's 12 possibilities. And if you draw a tree diagram, it actually will help you see this, okay? the first event is the heads or the tails. There's two possibilities. And then after you get the coin, you're either going up the head or the tail path. Then you have the die, which is going to be either a 1, a 2, a 3, a 4, a 5, or a 6. So you see what's going on here? If you look over here, you can kind of see, well, I got a head and a 1, a head and a 2, a head and a 3, and down here I've got a tail and a 1, a tail and a 2, and so forth. But I think it's hopefully it gets reasonably clear. It's 2 times 6 is equal to 12. That's the number of possibilities. How about the paints here? Let's talk about paints. There are different, and using this language here, there's K1, K2, K3, however many there are. There's a certain number of events, and each event has K1 or K2 or K3 possibilities. So here we go. We're picking the paint. We're going to manufacture the paint. For the color, that is the first event. There's 1, 2, 3, 4, 5, 6, 7. So there's 7 possibilities for that first event of picking the color. Well, so K1 is, what did I just say? 1, 2, 3, 4, 5, 6, 7. So K1 is 7. K2 is the second choice we have to make. That's the second event. That's latex or oil. So that's 2 possibilities. The third is the texture. So there's 1, 2, 3, 4. Oh, no, I'm sorry. 1, 2, 3. So there's 1, 2, 3. So K3 is 3, and so forth. So how many different types of paints can you make? So it's very useful sometimes to draw these little boxes and to say, okay, there's 7 possibilities, 2 possibilities, 3 possibilities, 2 possibilities. Multiply all these guys together and you get the 84. Okay, so there's 84 possibilities out of these choices that you can come up with. So you could have 84 different types of paint in your store. All right, one more example here. Distribution of the blood types. We have 4 different blood types. Okay, A, B, and O. You nurses in there can explain to us what the RH factor is. So you have RH plus or RH negative. Okay, and then finally you can classify them as a male or female. Now, drawing our little boxes, just like we did before, I believe makes it a little bit more clear. So that I have a blood type, you have 4 choices. RH, you have 2 choices. Gender, you have 2 choices. Multiply them together, you have 16 possibilities. So here we have K1 is 4, K2 is 2, K3 is 2. So we multiply them together. Here's a tree diagram that actually, I believe, helps make sense. Let's just pick one. Let's say we get the B first. That's the B corresponds to the blood type. After we get down this okay, pardon me for the interruption. After we get down this line segment, this is the one where we've chosen the B. Okay, there's 1, 2, 3, 4 possibilities. We go down this one, the B line segment. That corresponds up here to the blood type going down the B. I'm not sure what this author calls it. The B, this path or this line segment. It's basically a path, right? It's going down this path. Well, after we've gone down the path of B, now we have RH positive or RH negative. Let's suppose we go down RH positive. Well, now we have another path we have to choose, male or female. So as you can see, these are all the possibilities, which would be very tedious to write those all out and then have to count them. It's much easier to just know this fundamental rule, which says you multiply these guys together. So I hope that helps you understand that. Okay? Okay, so now here's an important point. When you determine the number of different possibilities of a sequence of events, you must know whether repetitions are permissible. So it's either, sometimes the author will call this repetitions, and sometimes the author will call it replacement. So the two terms kind of basically mean the same thing. You're either repeating the same outcome, or you can also say you are replacing whatever it is that you're dealing with. So for example, when we were dealing with the urns, if you take out or I'm sorry, balls, okay? The balls are inside the urns. If you pull out a blue ball, if you put it back in, you're replacing the blue ball. Another way of saying that is you could say, well, I have repetitions. So repetitions and replacement are kind of the same basic concept. So we need to know whether or not we have repetition or not, or replacement or not. Okay, so we got these license plates, okay? We have 4 digits. Assuming that the repetitions are allowed, how many memorial plates should be issued? So there's 4 spaces to fill. So there's 10 digits, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 10 possibilities. So 10 times 10 times 10 times 10. It's because there's 4 digits, 4 little boxes that we would fill in. Now, that's if the repetitions are permitted. We do have replacement. We have replacement in the sense that we take a number, but we put the number back in the pot. We can pick out that number again. But let's suppose we do not allow for repetitions. Suppose we do not allow. The first digit of the plate could be selected in 10 ways. Well, whatever number you pick, the second digit there's not 10 choices anymore because you've already picked one. So you only have 9 choices. Well, then for the next one, you've already picked 2 numbers, so you don't have 10 digits to pick from. You don't have 9 digits to pick from. You only have 8 digits to pick from. If that's not clear, write out an example for yourself and it will become abundantly clear. So now we have, instead of 10 times 10 times 10 times 10, we have 10 times 9 times 8 times 7. He's missing a little dot there. So 10 times 9 times 8 times 7, that's 5,040. Okay, so it's the same exact situation as if you're drawing balls from an urn or whether you're drawing cards from a deck. If you replace the ball, if you replace the card, we say that we have repetitions. Okay, the repetitions are permitted. Okay, so, all right. If repetitions are permitted, then the numbers stay the same going from left to right. So it would be this 10 times 10 times 10. If repetitions are not permitted, you cannot have the same number, again, then the numbers decrease by 1 for each place left to right. Okay, so now, in my humble opinion, I don't like memorizing rules. I think if you memorize this rule, you're going to forget it in a moment of stress. Just think about it and just recognize that, well, of course, if I don't have repetition, every time I pick somebody, I have 1 less to pick from in the next little box, okay? All right, so that's the fundamental rule. So that's the end of this video. Next, we're going to talk about these other concepts of permutations and combinations. So I'll get to that here in the next video.